So today we're going to look at some special properties of symmetric matrices and what it actually looks like when we diagonalize them. So remember, when you diagonalize a matrix, you're saying that it is similar to a diagonal matrix. So we can find this diagonal matrix D, and we'll find this matrix P that is invertible such that A is equal to PDP inverse. Now we know that when we have a diagonalizable matrix, it means that for each of the eigenvalues of A, it has the same dimensional eigenspace as each one of the multiplicities of the eigenvalues. So we know when a matrix is diagonalizable, but we want to look in particular at a special property of this matrix A, and that is when it is symmetric. So what happens when A is symmetric? So that means that A is equal to A transpose. Okay, if a matrix is symmetric, it means that it is symmetric across that main diagonal. So the main diagonal that goes from the top left corner to the bottom right corner, that diagonal on that matrix can be whatever it likes. But the entries that go across that main diagonal have got to be the mirror image of one another. Okay, so if you've got a 2 in the 1, 2 position in the matrix, in the 2, 1 position of the matrix, you've also got to have a 2. So it's symmetric across that main diagonal. That means that when you transpose the matrix and each one of the rows becomes a column and each one of the columns becomes a row, you're going to end up with the same matrix. So we want to know what happens when a matrix is symmetric. Now, for a start, because A is equal to A transpose, it means that you've got to start out with a square matrix. But we already know that with square matrices, like, you've got to have a square matrix in order to diagonalize it like this, because otherwise you can't find eigenvectors and eigenvalues. So we're already looking at square matrices. Okay, so this thing has to be square. Let's take an example of a matrix, and we're going to try and diagonalize this thing. So let's say that A is 1, -6, 4, -6, 2, -2, 4, -2, and -3. Okay, you could see that along that main diagonal we have 1, 2, -3. That can equal what it likes. But if we look at the entries on either side of the main diagonal, okay, I've got -6s there, I've got 4s there, I've got -2s there. So it's symmetric across that main diagonal. Okay, so if you were to transpose this matrix, you would again get the matrix A. Okay, let's go ahead and diagonalize this thing. So let's get it into the form A is equal to PDP inverse. Okay, I'll tell you what the eigenvectors and eigenvalues are. The eigenvalues are -3, -6, and 9, and then the corresponding eigenvectors for each one are these. I'll call them V1, V2, and V3. Okay. So I've got the 3 eigenvalues. They're actually distinct in this case, and then I have the 3 eigenvectors. So I already know that D, that diagonal matrix, is a diagonal matrix with those eigenvalues on the main diagonal. Okay. Now, what you could do is you could say, okay, P is equal to the matrix that has each one of these vectors as a column. That's what we normally do, and then P inverse goes on the other side of D. That's fine. You could do that. That's totally fine. But what you will notice, if you look at each one of these eigenvectors, number one, we already know that they're linearly independent. Okay, we know that eigenvectors are linearly independent. We did that back in chapter 5. But what we can actually see here, if you look at this, if I were to take the dot product of any 2 of these vectors, so let's say I did the dot product of V1 with V2, I end up with 0. Same thing as when I take the dot product of V1 with V3, I again get 0. And V2 with V3, I get 0. So, not only are these vectors linearly independent, they are actually orthogonal to one another. The eigenvectors are orthogonal. Okay, so they're linearly independent and they're orthogonal. Okay. However, what I would really like for that matrix P, just to make things, it doesn't necessarily look nicer, but it can help us out with some calculations further down the road, I would actually like to make these orthonormal to one another. So I want to take these three vectors and I want to normalize them, divide each one by its magnitude. Okay. What that will then give me is an orthonormal matrix P. Then I'll have the diagonal matrix D, and then I can take P inverse, which again will be an orthonormal matrix. So what I'm going to have, if I normalize each of the vectors, okay, I'm going to end up with my matrix P as each one of these normalized columns. So I'm going to take V1 as my first column of P, but I'll normalize it first. If you take the magnitude of that vector, it's actually 3. So I'm going to end up with my first column is 1 over 3, 2 over 3, 2 over 3. Do the same thing with the next column. Okay, normalize that column, and that will be your second one. And then finally, for the third column, I'm going to end up with 2 over 3, negative 2 over 3, 1 over 3, okay? As I said, you could have taken P to equal the matrix with those orthogonal vectors as columns. That's totally fine. It still works with PD, P inverse. All I have done here is divided each one of those vectors by its magnitude, and you would actually find that when you took P inverse, all of that will cancel itself out anyway, so it doesn't actually matter if you take the orthogonal or the orthonormal. But with some of these calculations coming up, I want these to be orthonormal, okay? It makes my life a lot easier with what I'm about to do, okay? But in terms of actually diagonalizing the matrix, you could leave P with the orthogonal vectors, that's totally fine. They're linearly independent, that's all we worry about. But with what I've got coming up, I want these to be orthonormal, okay? So I'm going to take P as that, and then D, as we said, would be our matrix from before, negative 3, 0, 0, 0, negative 6, 0, 0, 0, 9. And then A is equal to PD, P inverse. Now, this is something that is mentioned in your homework from technically this week if you're watching this on time. If not, if you're watching it later, it will be in last week's homework. But the homework that you have for Friday, May 1st, you have a problem in there that looks at orthogonal matrices. I actually personally define orthogonal matrices slightly different to what this textbook defines it as. So you came across this when you did the homework. The way that they define orthogonal matrices is a matrix is orthogonal if it is an orthonormal matrix that is square, okay? And it has the property that U transpose equals U inverse. We already know from orthonormal matrices that U transpose U is equal to I, okay? So what they have said here, if a matrix is orthogonal, it means that it satisfies this, but the matrix U is square, okay? So if you think about this matrix U that has, it's orthonormal, which means it has orthonormal columns, we know it satisfies this. If it has orthonormal columns, therefore the columns are orthogonal to one another, so they must be linearly independent. So if this matrix U has these linearly independent columns, but U is also square, I know that U is invertible. So that means if a matrix is both orthonormal and square, I can invert U. So I can say that U transpose is equal to U inverse. So that is where this comes from. So an orthogonal matrix is just an orthonormal matrix, so a matrix that has orthonormal columns, but it is also square, okay? Coming back to what we have here, okay? If we have a matrix that has this property that U transpose is equal to U inverse, that means it has orthonormal columns and is square. Well, that is true of this matrix P, okay? P has orthonormal columns because of the way that we just constructed this, and it is a square matrix. So I know that P inverse can also be written as P transpose. Okay. That makes this much easier to calculate. Okay, when you diagonalize this matrix A, when A is symmetric, we now know that we can create this P out of these orthonormal eigenvectors of A. And therefore, it makes P not only this invertible matrix, P is now actually an orthonormal matrix, and not just that, it's actually an orthogonal matrix because it is also square. So I know that P inverse can be very easily calculated just by transposing that matrix P, okay? Just as an added side note, because here you have this square matrix, you know that the columns are linearly independent. Each one of these eigenvectors can be put into a basis, and they actually form an orthonormal basis for R3 in this case. So you have these three linearly independent vectors that are orthonormal to one another, which means that they are also linearly independent, which means that because you have three of them, they're going to form a basis for R3. Okay, just as an added side note. So, what we have seen here, okay, so far, is if A is symmetric, then any two eigenvectors from different eigenspaces are orthogonal to one another. Okay, so what we have looked at here, okay, we have this symmetric matrix A, okay, so it's symmetric about that main diagonal. Then if I take any two eigenvectors such that they come from different eigenspaces, so they can't come from the same eigenspace that's related to that same eigenvector, or the same eigenvalue, sorry, okay, so you can't, if you come back here, okay, for each one of my eigenvalues, I took an eigenvector, okay? But if I take two different eigenvalues and take their associated eigenvectors, those eigenvectors are always going to be orthogonal to one another. This only happens when A is symmetric. The question is why? Okay, I mean, we could see it in this example, but why does this happen? Okay. Well, let's say that I've got two distinct eigenvalues. Let's say you've got lambda 1 and lambda 2 are both distinct, okay? So lambda 1 does not equal lambda 2. And take an eigenvector from each one of their eigenspaces. So from the eigenspace of lambda 1, I'm going to take v1, and from the eigenspace of lambda 2, I'm going to take v2. Okay? If I did lambda 1, v1 dot v2, okay? I want to come out at the end of this with v1 dot v2 is 0, okay? But I've got some work to do first. You know that if you take the dot product of two vectors, it's the same thing as taking the transpose of the first vector multiplied by the second vector. So this thing can also be rewritten as that, okay? I'm going to rewrite this slightly, okay? You can, this lambda 1 is just a scalar, okay, if you think about it. So if I transpose a scalar, I'm going to get the same thing, okay? Transposing a single number doesn't move it anywhere, okay? If you take the transpose of a product, it's the same thing as taking the product of the transposes, but in reverse order, okay? So what I could actually write this as, I'm going to rearrange this formula slightly before I do this. This lambda 1 is a scalar. It can be moved anywhere in this equation, okay? And if I transpose that lambda 1, it's not going to change the value of it. It is just a scalar. So I can also rewrite this as v1 transpose, lambda 1 transpose, v2, okay? So I've just moved that lambda 1, and I've transposed it, which won't change anything, okay? So I now have the product of two transposes. That is the same thing as taking the product of those two elements in reverse and transposing it. So that's the same as that, okay? Now, lambda 1 v1. v1 is an eigenvector of A with eigenvalue lambda. So I know that this thing is the same as saying A v1 transpose v2, okay, by AV is equal to lambda v for any eigenvector and eigenvalue. I know that that can be rewritten as that, okay? Now, again, I've got a product transposed. So that's the same thing as taking each one of these transposed but in reverse order. So I can rewrite that as v1 transpose, A transpose, v2. Now, A is symmetric. We said that up the top. So A transpose is just A. So that's the same thing as saying that, with A transpose is equal to A. Now, AV2 is just lambda 2 v2 by our eigenvectors and eigenvalues formula. So this is saying v1 transpose lambda 2 v2. I'm going to basically undo this equation in the same way that I did up the top here. Okay, so I'm going to rewrite this. I'm going to take the lambda 2 out the front, and then v1 transpose v2 is just the dot product of the two vectors. So that's going to be lambda 2 v1 dot v2. So that tells me that lambda 1 v1 dot v2 is equal to lambda 2 v1 dot v2. So let's rearrange that, bring it all onto one side and factor out the v1 dot v2. Okay, so one of these two things has to be 0. We know that this first thing cannot be 0 because lambda 1 and lambda 2 are distinct. That tells me that v1 dot v2 must equal 0. So they are orthogonal to one another. So if you ever take two eigenvectors from two different eigenspaces for a symmetric matrix A, they're going to be orthogonal to one another. Okay. So there is actually a definition to put all of this together. An n by n matrix A is something called orthogonally diagonalizable. Okay, it's got a long name. Orthogonally diagonalizable if we can find this orthogonal matrix P. So it's this orthonormal matrix that's square. So we know that for an orthogonal matrix that the transpose of the matrix equals the inverse of the matrix, where A is equal to P D P inverse, which is the same thing as saying P D P transpose. Okay, so it's orthogonally diagonalizable if we can find these eigenvectors of A that are orthogonal to one another, and we know that this matrix is diagonalizable. So each one of the multiplicities is equal to the dimension of the eigenspace. Now, as we've seen here, this happens when A is symmetric. But does it happen both ways around? So if we assume that A is symmetric, is this true? And is this true if A is symmetric? The answer is yes, because if I take A transpose, where A is equal to this thing here, that's P D P transpose transpose. When you take the transpose of a product, it's the same thing as taking the product of the transposes in reverse. So I would have P transpose transpose, which is just P. Then I would have D transpose P transpose. D is a diagonal matrix, so taking its transpose just equals itself. And that is A. Okay? So a matrix is orthogonally diagonalizable if and only if A is symmetric. Okay. So the only time that we can find this PDP inverse, where P is an orthogonal matrix related to A, the only time that we can do that is if and only if A is symmetric. Okay. Now, that's great, but sometimes we can run into problems. Okay. We saw in our first example it was super easy to do this and to orthogonally diagonalize this matrix, okay, because we started out with these 3 eigenvalues and the 3 eigenvectors. It was super easy because they were already orthogonal to one another, so all we had to do was normalize each of the vectors and put them into this matrix P. The problem comes when you have repeated eigenvalues. Okay, because it's super easy when they're distinct, as we can see here, because they already end up being orthogonal to one another, because we know that eigenvectors from distinct eigenspaces, so related to distinct eigenvalues, are going to be orthogonal to one another. We've already proved that. The problem comes when you are looking within an eigenspace where that eigenvalue is repeated, because the eigenvectors that come out may not be orthogonal to one another. So you have to do some work in order to make these 2 vectors orthogonal to one another, and therefore they will then be orthogonal to all the other vectors. So I'm taking this example out of the textbook because the numbers worked out nicer than some other examples I found, so I want to make sure that the example that I choose comes out with decent numbers. So I'm actually doing this example that comes from the textbook. I want to orthogonally diagonalize the matrix A is equal to 3, -2, 4, -2, 6, 2, 4, 2, 3. Okay. Again, this is a symmetric matrix. It's symmetric about its main diagonal. And I know that if I take the transpose of the matrix, I get the same thing. So I know that I can orthogonally diagonalize this thing. If you go ahead and find the eigenvalues and eigenvectors of this matrix, you find that the eigenvalues are lambda is equal to 7 and lambda is equal to -2. Okay, this eigenvalue, lambda 1 is equal to 7, is a repeated eigenvalue. It has multiplicity 2, which means it has 2 eigenvectors that are associated with it. Okay, it has these 2 eigenvectors, and then this eigenvalue here, lambda is equal to -2. This has eigenvector, we'll call it V3, which is equal to that. Now, you can see that V1 is orthogonal to V3 and V2 is orthogonal to V3, because when you take the dot product of those, you're going to get 0. The issue comes when you take the dot product of these 2 vectors, V1 with V2. You do not get 0. So, these are not orthogonal to one another. So, we need to do some work to find 2 vectors in this eigenspace that are orthogonal to one another and hence orthogonal to all the other vectors from the other eigenspaces. Okay. So what I want to look at, if we take the space that is spanned by these 2 vectors, they are linearly independent from one another, so we're going to get this plane. Okay. It's going to be a plane in R3 that they're going to span. We need to find 2 vectors in that space that are going to be orthogonal to one another. We'll start with V1, okay? We'll keep that one as it is. And then I want to adjust V2 in such a way, using our orthogonal projections that we looked at in 6.3. I'm going to find this vector that is orthogonal to V1, okay? And then they are still going to span that eigenspace, but they're going to be orthogonal to one another, okay? You can go ahead and do this using the Gram-Schmidt process, okay? To find this vector that is going to be orthogonal to V1, okay, you can say, we'll call it, I think I called it Z2 actually when I did this. We'll call it Z2. It's going to be my initial vector V2 that I've started out with minus the projection of V2 onto the line spanned by V1. which is going to be v2 dot v1 over v1 dot v1 times v1. Okay, so that is the projection of v2 onto the line spanned by v1, and then this vector here, z2, is actually orthogonal to that line, okay, by taking v2 minus the projection of v2 onto that line spanned by v1. Okay, we looked at this in 6.2 and 6.3, okay, and then we use this Gram-Schmidt process of changing this basis for that space. Okay. So, if you went ahead and did this, the vector that I end up with is negative 1 over 4, 1 over 4. Okay, you can go ahead and do this by taking v2 and then taking the dot products and then multiplying that by v1. You should end up with this vector. Okay, so I now know if I take the two vectors v1 and my new vector z2, okay, I'm going to get 1, 0, 1, negative 1 over 4, 1 over 4. Okay, these two vectors, they span the eigenspace, okay, by construction when we did these orthogonal projections in our Gram-Schmidt process of finding this new orthogonal basis for a space. Okay, they span the same space that v1 and v2 did, but they are now orthogonal to one another, because if I take the dot product of these two vectors, I'm going to get 0. Okay, and then I can normalize these two, and I can normalize my third vector, v3, that was associated with the other eigenspace. I'm going to take the orthonormal basis, so I'm going to normalize each one of those three vectors, and then I'm going to put that into my matrix P. So when you do that, so I'm going to first normalize both of these vectors, so I'm going to get 1 over the square root of 2, 0, 1 over the square root of 2. What I'm actually going to do to this vector, just to make it easier to normalize, is multiply the whole thing through by 4. That's not going to change the fact that it's orthogonal to this vector here. Okay, they're still going to be orthogonal to one another. I'm just taking a multiple of that eigenvector. It's still in the same eigenspace, and it is still going to be orthogonal to the other vector. Okay, and then I can go ahead and normalize. It's just way easier when dealing with these fractions. So if you do that, so if you multiply the vector through by 4 and then normalize, you end up with negative 1 over the square root of 18, 4 over the square root of 18, and 1 over the square root of 18. And finally, our other eigenvector was this. So I'm going to do the same thing here, just so I don't have to deal with too many fractions going on. I'm going to multiply the whole thing through by 2 to make sure that everything is a whole number, is an integer, and then I can go ahead and normalize. So if I do that, so multiply through by 2 and then normalize, I end up with negative 2 over 3, negative 1 over 3, 2 over 3. Okay. All of these, like all these three vectors, they are orthonormal to one another. So if I take the dot product of any two of them, I'm going to get 0, and each one has magnitude 1 now. Okay. So I've put them into this matrix P. It makes an orthogonal matrix. It's an orthonormal matrix that's square. And D is 7, 0, 0, 0, 7, 0, 0, 0, negative 2. And A is equal to P, D, P inverse, or alternatively, P, D, P transpose, as I know that P is an orthogonal matrix. All of this can be put into a theorem, and it's called the spectral theorem for symmetric matrices. The reason it's called the spectral theorem is because you tend to call, there's like another name for eigenvalues of a matrix. You can call the eigenvalues of a matrix the spectrum of a matrix. So that's why it's called the spectral theorem. You don't have to worry too much about that. But the spectral theorem for symmetric matrices. What this theorem tells us is that there are 4 things actually that are equivalent to one another. Okay, these are 4 properties of symmetric matrices that, of course, are square. So for an n by n symmetric matrix A, Okay. First thing is that A has n real eigenvalues. Okay. They may not all be distinct, but it's going to have n eigenvalues. Okay. Then, secondly, you're always going to find that this matrix is diagonalizable, okay? Each of the multiplicities of the eigenvalues is going to equal the dimension of the eigenspace. You are never going to come across a situation with a symmetric matrix where you cannot diagonalize it. So you're not going to get some eigenvalue that has multiplicity 3, but its eigenspace only has dimension 1 or 2, okay? It's always going to have matching multiplicity to the dimension of the eigenspace, okay? So the dimension of the eigenspace for each lambda equals the multiplicity of lambda, okay? Then, not only that, but coming back to a theorem that we looked at just now, okay, for each of the eigenspaces, okay, that relate to a distinct eigenvalue, they are orthogonal to one another. So each one of the eigenspaces for each one of the distinct eigenvalues gives a space that is orthogonal to the other eigenspaces in A. Okay. Each of the eigenspaces relating to distinct eigenvalues are orthogonal to one another. Okay, that's simply because we know that the eigenvectors relating to distinct eigenvalues are orthogonal to one another, therefore the whole eigenspace is actually orthogonal to the other eigenspaces. And putting all of that together, A is orthogonally diagonalizable. Now, we can actually write this orthogonal diagonalization for a symmetric matrix A in a slightly different way, and it's something called the spectral decomposition of this symmetric matrix. We know that for a symmetric matrix A, it's orthogonally diagonalizable. So not only is A equal to PDP inverse, A is actually equal to PDP transpose. Okay. I'm going to write this slightly differently, so I'm actually going to expand this out. Let's say that each one of the columns of P, so each one of those orthonormal columns, I'm going to call them U1 through UN. Okay. Then the eigenvalues of A, I'm going to call lambda 1 through lambda n. They may not be distinct, but we'll call them lambda 1 through lambda n. And then P transpose is just going to be this matrix here transposed. So I'm going to take each one of U1 through UN as the columns, and I'm going to turn them into rows. So my first row of P transpose is U1 transpose, and my last row is going to be UN transpose. Okay. Then you'll notice that when you take P multiplied by D, okay, this has got zeros all above the diagonal and all below the diagonal. When you take P multiplied by D, the only thing that is ever going to multiply an element in U1 is lambda 1. Okay, when you do row in P times a column in D, the only thing that is ever going to hit U1 is lambda 1. So I know that I can write this as lambda 1, U1. The only thing that's going to hit U2 or lambda 2 is the other one. So I know that the only thing that lambda 2 will hit is U2. So my second column would be U2 is lambda 2, U2. Same thing, the only thing that's going to hit UN is lambda n. So my last column is lambda n un. And so my final column then is still this u1 transpose un transpose. Again, when we do row times column, the only thing that is going to hit lambda 1 u1 is this u1 transpose. Okay, the only thing that my first column hits is going to be my first row when I do row times column. Okay, the only thing that my second column is going to hit is my second row, u2 transpose. So when I do this and I do row times column, what I actually end up with is lambda 1 u1 times u1 transpose plus lambda 2 u2 transpose up to, oh, I should have done that. Let me come back. Plus there, plus, and then lambda n un transpose. Okay. Each one of these, okay, I've got a column vector times a row vector. So when you end up doing row times column to figure this out, you actually get an n by n matrix in each case, which makes sense because I'm taking a scalar times an n by n matrix plus a scalar times an n by n matrix, etc. That will equal an n by n matrix, okay? I can't have a ton of vectors added together equal to an n by n matrix. It doesn't make sense. So each one of these where I've got a column vector times a row vector will actually give me a whole matrix. Okay, this is called the spectral decomposition of A. Okay, so what it does is it takes each one of the eigenvalues and each one of the orthonormal eigenvectors associated with it, and it splits it up. Okay, if you actually think about this, when you take A times a vector, okay, so A times X, each one of these will give you a projection of that vector onto the space that is spanned by that ui. Okay, if you go back to the end of 6.3 where we looked at the projection of y onto a space w, it was equal to that u transpose y, where each one of the columns of u was a basis vector for that space w. Okay, exactly the same thing here. It's just that each time you are projecting it onto a one-dimensional subspace, okay? And then you are adding them all together. So if I take a vector x and I multiply it by a, it's the same thing as taking a projection of x onto each one of these one-dimensional subspaces, u1 through un, and then adding them all together. Okay, so you can just see it multiplying by this symmetric matrix A is the same thing as taking a bunch of one-dimensional projections and adding them all together and seeing where it lands. Okay, that is the end of 7.1. Next time we're going to carry on with this and look at quadratic forms, but it's just an extension of this. If you have any questions, let me know, and I will see you in the next video.